Brake Fundamentals, Part 2. Factors governing braking power. There are four basic factors that determine braking power of the system. The first three factors governing the generation of friction, pressure, the coefficient of friction, and the friction contact surfaces. The fourth is a result of friction, and that is heat. Pressure. The amount of friction generated between the moving surfaces contacting each other depends on the pressure exerted on the surfaces. Try this. Place your hand on the surface of the table and slowly increase the downward pressure of the palm of your hand as you move it across the table. You will feel a gradual increase in friction. In an automobile, this pressure is provided by the hydraulic system. This hydraulic force is used to move the brake pads and or brake shoes against spinning drums and rotors. The coefficient of friction, or COF, is a measurement of friction between surfaces. It takes more force to stop some objects across a surface than others, even though applied pressure and the amount of surface in contact are the same. Different materials have different frictional characteristics or coefficients of friction. It is easier to slide a 100-pound piece of ice across a metal surface than a 100-pound piece of rubber. This slide depicts that it takes 100 or 1 pound of the coefficient of friction to slide rubber, and it's 2/10 of a to do the same with a block of ice. The ideal coefficient of friction is about 0.33. At this level, the brakes can be applied smoothly and stop the vehicle. If the COF is too low, the vehicle will stop too slowly. When the COF is too high, the brakes will lock up too easily. The amount of friction between two surfaces and thus the amount of heat generated during braking is determined by three main factors. The composition of the surface. Some materials are stickier than others. The condition of those surfaces. Rust, corrosion, or scoring has a significant effect on friction. The pressure applied to those two surfaces. The greater the pressure, the more friction and heat are generated. Frictional contact surfaces. The third factor is the amount of friction that is in contact. Simply put, bigger brakes stop a car more quickly than smaller brakes used on the same car. Similarly, brakes on four wheels stop the car more quickly than two, assuming the vehicles are of the same size and weight. Heat dissipation. Any braking system must be able to efficiently handle the heat caused by friction within the system. The temperature in the brake linings can reach 600 degrees Fahrenheit during the stop. This is tremendous heat and is created by rubbing must be directed away from the pads and rotors or brake shoes and drums and absorbed by the surrounding air. The greater the surface area of the brake components, the faster the heat can be dissipated. Brakes do not effectively dissipate heat will experience what's known as brake fade during hard continuous braking. The linings will become glazed and the drums and rotors hardened. Therefore, the coefficient of friction will be reduced and excessive foot pressure will be required to stop with the desired braking effect. Brake lining friction materials. The friction materials used on brake pads and shoes is referred to as linings. Brake linings will either be riveted or bonded to the backing of the shoes or pads. Some newer types of pads are integrally molded. These are easily identified by looking at the back of the pad. If there are holes that are partially or totally filled with lining material, then you have integrated pads. For many decades, asbestos was the standard lining material. It offered good friction qualities as well as low noise. New materials are being used today because of health concerns of asbestos dust. In fact, federal government has banned its use in new and replacement shoes and pads. Types of brake lining. Fully metallic linings of cindered iron have been around for many years in heavy-duty and racing applications. That's because they have great fade resistance. However, they require a lot of pedal effort and tend to quickly wear out the drums and rotors. Semi-metallic linings were developed to eliminate the disadvantage of fully metallic linings. Semi-metallic linings are made out of iron fibers molded with an adhesive matrix. Semi-metallic materials offer excellent fade resistance that meets the needs of today's vehicles. It has good frictional characteristics, so only a moderate amount of pressure is needed. Semi-metallic pads and shoes do not cause excessive amounts of wear on pads, drums, and rotors. Other materials such as carbon metallic, ceramic pads, and shoes are available. Brake lining manufacturers are experimenting with new materials and meet well-established criteria for long life, friction characteristics, drum and rotor wear and heat dissipation. Since 1967, the federal government has required that vehicles be equipped with two separate braking systems. If one circuit were to fail, then there would be a backup to safely stop the car. The dual system differs from the single system by employing a tandem master cylinder, which is essentially two master cylinders formed by installing two separate pistons and fluid reservoirs in one cylinder bore. Each piston applies pressure to two wheels. This is a diagram of a dual master cylinder. You can see the primary piston, the secondary piston, and the reservoirs. This slide depicts a dual front-rear braking system. In early years of the dual system, the systems were split front and rear. Both fronts were on one circuit while the rears were on the other. So if one system failed, you would have the other to stop the vehicle. However, front brakes do about 70% of the braking, while 30% is done by the rear. So a failure of the front brakes would leave only about 30% of the braking ability to stop the vehicle. Front-rear split systems. The problem was somewhat reduced with the development of diagonally split systems. This system operates on the same principles as the front-rear split system. It uses a tandem master cylinder to simultaneously exert hydraulic pressure to their respective systems. The brake lines, however, have been diagonally split. This is that the right front, left rear is on one side, while the left front, right rear are on the other. So in the event of system failure, you will have one front, one rear braking, thus maintaining 50% braking power. Brake fluid. Brake fluid must. Brake fluid is the brake or the blood of the brake system. It is what makes the system operate properly. Modern brake fluid is blended to enable it to perform a variety of functions. It must have a high boiling point to prevent hydraulic fade. It must have a low freezing point so it does not freeze even in low temperatures. And it must lubricate moving parts such as pistons and seals. Modern brake fluid must be compatible with rubber to avoid damage to rubber components within the braking system. Most brake fluids are based on alkali, polyglycol, ether esters, or polyglycol. Polyglycol is clear and to amber in color. It is a solvent that will dissipate paint on contact. Flush paint with water to remove spilled brake fluid. Have a low freezing point so it does not freeze even in low temperatures. Brake fluid. Modern brake fluid must be compatible with rubber to avoid damage to rubber components in the braking system. Today's fluid must meet standards set by the Automotive Society of Engineers, SAE, and the Department of Transportation, DOT. There are three main types of brake fluid: DOT3, DOT4, and DOT5. DOT5 is a synthetic brake fluid, while DOT3 and 4 is a polyglycol based, similar to engine coolant. DOT5 is a synthetic brake fluid, while DOT3 and 4 are polyglycol based, similar to engine coolant. Purple in color and typically used on show cars or other specific applications. It is not corrosive to paint, but will have a higher affinity for air than polyglycol. And it is not compatible with polyglycol based fluids. DOT5 is a unique silicone-based brake fluid with an equilibrium reflux boiling point of 500 degrees Fahrenheit and a wet ERBP of 356 degrees Fahrenheit. DOT3 is a conventional brake fluid with an ERBP of 401 degrees and a minimum wet ERBP of 284 degrees Fahrenheit. This is generally recommended for most ABS systems and power brake setups. DOT4 is a conventional brake fluid with an ERBP of 446 degrees Fahrenheit and a wet minimum of 356 degrees Fahrenheit, and is the most common brake fluid used in modern braking systems. DOT5 is a unique silicon-based brake fluid with an ERBP of 500 degrees Fahrenheit and a wet ERBP of 356 degrees Fahrenheit. There is a new brake fluid out, DOT5.1, which is also polyglycol and is used in some Ford systems. Make note, use only approved brake fluid in a brake system. Any other lubricant, such as power steering fluid, automatic transmission fluid, or engine oil, which is petroleum-based, will react with the rubber components of the brake system and cause them to swell and disintegrate. Some vehicles have fluid level sensors that provide the driver with a message when the brake fluid is low.